We are now in chapter 3, and in chapter 3 we're going to talk about linear and quadratic functions. The first section of chapter 3, and by the way, these are the sections. We're going to look at only these 3 sections. Sections 2 and 4 are left out, and that's on purpose. So let's begin with chapter 3, section 1. In section 1, we're going to look at some properties of linear functions. Okay, so what properties are we talking about? First of all, I want to emphasize that our focus is on linear functions. Now, the general form of linear functions, these are functions that are in the form f of x equal to, we're going to go mx plus b, just to stay with the form of a linear equation. Remember from your elementary algebra, y equal mx plus b was the equation of a line, correct? Where m is the slope and b is the y component of the y-intercept. Okay, so let me just write that. So this would be the y-intercept, they call it, but really the intercept is at 0b because it is a point. So together we're looking at the point slope form of a line. And here's a linear function. It looks very much like the linear equations. Now the role that m plays here, the slope, let's take a look at the possibilities for slope. So for example, this would be the case where the slope of the line is positive. If the slope's negative, the line is going to be oriented in that direction. Remember, the slope gives you the orientation or the steepness of a line. And if a line has a slope 0, that means there is no change in y as x changes. Okay, so we're looking at some possibilities with the slope of a line. Now, vertical lines, of course, have no slope. So here we say slope is undefined for vertical lines. And it has to do with definition of a slope. So let me go back to write the definition of a slope. We use m like the book does. Formally, slope of a line is defined as the change in y over change in x, correct? Now the change for us, we're going to use a new notation, delta. Delta y, capital delta, and capital delta x. So remember, delta here means change. Delta y means change in x, change in y. There are 2 deltas in Greek alphabet. This is one of them. The other delta looks like that. Both of these are deltas. In your calculus courses, you deal with the other version of delta when they define limits of functions. Okay, so that's what we have. Now, that's about all as far as the slope of a line or a linear function is concerned. It is worthwhile to mention that if the slope of a line is positive, then the linear function is increasing. If the slope's negative, the linear function is decreasing. And that means it is falling. The other case is when it's rising. So we can actually write that one as well. And if the slope of the line is 0, the function is neither increasing nor decreasing, right? That's where we have a constant function. So I'm just going to put decreasing, and this one is going to be constant. All right. Now let's pursue this idea of a change in y and change in x. So suppose, for instance, let's say I have some, and I'm going to choose a non-linear function. Functions that are not linear, if they're not a linear function, then we call them non-linear. Anything other than linear is called non-linear. So I'm making up some non-linear function here. Okay, and I'm just going to choose some starting point x1 here and another point on that non-linear curve x2. The y value here is y1, and the y value at x2 is going to be y2, correct? Now we know that y1 is f at x1 and y2 is f at x2. Okay, now if I look at the change in the function, from point x sub 1 to x sub 2. And in between, of course, you can see the curve, the function is changing at a different rate. True? But if I look at the overall, from starting point to ending point x2, and that's given by that slant line, which we call the secant line. A secant line is a line that connects 2 points on a nonlinear function. Now, the distance from x1 to x2, that's going to be the change in x, right? That's this far. And the change in y is going to be this much. And therefore, I have the change in y over change in x as I go from x1 to x2. That the ratio of these two is what we call the average rate of change of the function. So I'm going to write the average rate of change of f of x is going to be simply delta y over delta x. All right. And that's all that is. Now, when it comes to linear functions, let's actually redraw this thing for a linear function. So my function now is a linear function. And same scenario, we're going to go from x1 to x2. And this is going to be y1, and this is going to be, let's say, y2. So the change in x is delta x, and the change in y, this much, is delta y. And I'm sure most of you recognize that if I take the ratio of delta y to delta x for the linear function, right, and this is f of x, mx plus b now. If I calculate that rate of change, delta y over delta x, that's simply the rise over run, isn't it? This is the rise, and this would be the run as I go from lower to higher point. So that's the very definition of a slope. So I can say that the slope of a line, which is m, is given by delta y over delta x. Now for the linear function only, the change in y would be y2 minus y1 over x2 minus x1, which is, this part is of course for all of them. What I meant for linear function only is this. Y sub 2, I'm going to change it to f of x sub 2. Again, that's still just a change in notation. You can do that for any function. And now for linear function. For the linear function, f at x sub 2, what does that mean? That means m x sub 2 plus b, right? The slope-intercept form at x sub 2 minus m x sub 1 plus b. So that part is for linear functions only. The ones above, what I have up here, this applies to all functions. Now, we can do a little bit of simple algebra here. If I remove parentheses, I get m at x sub 2 plus b minus m x sub 1 minus b. We got a couple of opposites, they add to 0. And the next step, I can actually factor in the numerator the factor m. That will give me x sub 2 minus x sub 1 divided by x sub 2 minus x sub 1. And now we can cross the common factors. That's equal m. Okay, so, well, what did we just show? Because we started with m, we ended up with m, so it looks like, okay, what does that mean? Well, remember, this was the average rate of change. Therefore, for a linear function, the average rate of change is the same as the slope. If f is linear, the slope is equal to the average rate of change. That's not true for other functions. So if a problem asks you to find the average rate of change, you simply find the slope. So let's take a look at an example here. For instance, in my example, suppose my function, linear function, is f of x is equal to negative 3x plus 4. And from this, what is the slope? Well, the slope is m, negative 3. The number that multiplies by x, that is the slope. What is the y-intercept? The y-intercept It's going to have coordinates as 0, 4. Some say 4 is the y-intercept, but again, as a point, it's got to have x and y, correct? Now, let's use the slope and y-intercept to graph this function, by the way. See how that is done without doing a t-chart. We don't want to do it this way, like negative 1, 0, 1. Don't want to do it that way. So if you want to use the slope and y-intercept to graph a linear function, you start at the y-intercept here, 1, 2, 3, 4. Correct? And then the slope, if the slope's negative, here's how I can write negative 3, by the way. I always write negative slopes like this as a negative number over 1, 1 being positive. Now I'm thinking in terms of rise and run, like we always do. So m is equal to negative 3 over 1. That means for a rise of negative 3, well, a rise of negative 3, you're actually falling, correct? You're going down 3. And the run is positive 1. So a positive run means you go to the right. That would be a second point on the graph of this function, correct? Okay. And right in here, we can connect the dots. And we get our linear function this way. So this is using the slope and y-intercept to graph that linear function. All right. And of course, domain of these linear functions are all real numbers. Okay. Now in this case, the function is indeed decreasing because the slope's negative. Right, since slope is negative. All right, and that takes care of that example. Let me do just one more example and we'll be done with this lecture. It's going to be a brief lecture. Now let's suppose my next example, I'm choosing a constant function f of x equal 4. And we know that from our library of function what the graph of this thing will look like. A constant function, so it's going to be a horizontal line at 4. There you go, call this 4 right there. That's a 0, and that's it. That's the graph of this function. Let's answer again the slope, the answer to the question, what is the slope? Well, it's a horizontal line, right? So notice as you go from one point to the next point, there is a change in x, there is a delta x, but there is no change in y. So slope is going to be, if I write it as delta y over delta x, delta y is 0, and whatever the change is doesn't matter. 0 over non-zero is 0. So slope's 0. What is the y-intercept of this constant function? Well, it crosses the y-axis at 4, so it's going to be 0, 4. Okay, in terms of increasing, decreasing, it's neither. The function is constant. So it's neither increasing nor decreasing. It's just flat lines. And what is the average rate of change here? 0. The average rate of change, which is the slope, correct, is 0. That means as you go from one point to the next point, there is no change in the slope of the secant line, in other words, because there is no secant line, there is no change. The average rate of change is 0 in the value of function. And again, you may say, well, how can that be? Well, as you go from x1 to x2, notice you move to the right, but the function, the y value, is not changing. No matter how far you go to the right or left, you're at the same level. Okay, and that will be it. As I mentioned, this will be a very brief lecture. So we're done with this lecture. Hopefully you can follow everything we've done in this section, and we are done.